Hey, okay, now we're live. The first time didn't work, but nobody knows about that, so I probably shouldn't have said anything. But we are live now.
We're professionals.
I don't have a producer today, so I'm doing it on my own. So what we're going to be doing this morning, I've been doing some of these math hangouts, and I said the other day that I'm going to try to do one to explain a little bit of matrix theory, very basic intro matrix theory. And I got Cheshire here,
okay.
and one of the reasons
Now
we're live. The first time didn't work, but nobody knows about that, so I probably shouldn't have said anything. But we are live now, and
We're professionals.
Oh my goodness. I don't have a producer today, so why am I hearing echo my own? And I know it's on my end. So what we're going to be doing this morning, I've been doing some of these math hangouts.
On the plus side, we weren't muted this time, yeah.
To explain a little bit of matrix theory,
but I don't know where it's coming from because I don't have the video open anyway.
And I got Cheshire here,
okay.
and one of the reasons
Now
we're live. The first time. I'll fix it. Give me 1 second here. I don't know where it's coming. I don't know where it's coming from.
Matrix theory and mathematics to someone with a 62 IQ. It's basically one of those YouTube challenges.
I don't know where it's coming. I don't know where it's coming from. I got an echo and I have no idea where this is coming from. It's really weird.
I can't help you.
I'm getting a loop, and I don't know where it's from because I got nothing open.
Apparently it stopped. Matrix theory and mathematics to someone with a 62 IQ. It's
no, but
basically
it
one of those
what
YouTube challenges.
For a sec. I don't know where it's coming. I don't know where it's coming from. I got an echo and I have no idea where this is coming from. It's really weird. And it's coming from my desktop audio. I will fix it, people. Give me a second. I can't help you. I promise. I'm getting a loop.
We believe.
And I don't know where it's from because I got nothing open.
We believe in Steve. We believe. Apparently it stopped. We believe in Steve. In theory and mathematics to someone. In Steve. Grab the glory.
I figured it out. Okay. Wow. You want me to start from the beginning or does it matter at this point?
Just go.
I just go with it. All right. So anyways, as Chess was trying to say that I've been trying to do this matrix hangout for quite some time, and I figured if I can explain it to Simp62 here, where she understands it, just about anybody can. So that's going to be the challenge, because she's never been exposed to matrix theory before. I don't think she's even had linear equations before. And so my challenge to me is, can I have a simpleton like Cheshire understand it? And well, it's going to be fun. Let's put it that way.
Thanks.
Yeah, no problem, man. So what we're going to be doing is a lot of people might know
I
how
have
to... Okay.
grade 11 math. That's it.
So you never even took college algebra then? This is all new to you. You are a virgin of this. We're going to basically de-virginize you.
Correct.
Okay. Now, bear in mind, people, I have not looked at this stuff really in 20, 30 years or whatever it's been, right? Since I took it, a little bit in college and had college algebra where we, did a lot of the... what you would normally do with matrix theory, like Gauss-Jordan, elimination, echelon shit. But we're not going to get that advanced. We're going to be doing very simple matrix theory to solve a two-system linear equation with two variables. And we're going to use what's called Cramer's rule.
So, with no context, he asked me, well, have you seen The Matrix? And I said, the movie?
That's not what I said. I said, are you familiar with The Matrix? And you're like, yeah, I've seen
the Matrix. The movie?
So you guys can see my challenge, right? You guys can see how difficult this is going to be for me, because it's not just explained to you guys. I can explain to her. So we got an treat feline out there, and she knows math, so she's going to keep me honest because she corrects my mistakes. But hopefully we're going to muddle through this. Again, it's going to be very intro because, again, I don't remember a lot from matrix theory, but hopefully I can remember this much. But let me kind of show you what we're doing visually. So Chess, this is kind of what we're going to be doing here. If you look on the outside, I have Desmos because I love Desmos. It basically is a great graphing program. And we're going to be solving basically the two variable system, meaning that has two variables, x and y. And we want to figure out what x and y are given two equations, in linear equations, which are going to be in the form of mx plus x, right? So it's not a parabola, it's nothing like that. It's just a straight line. A linear equation is a straight line, okay? Okay. So I just made up a linear system, and this was the linear system I just made up on the fly. for x or for y equals 18. So this would give me a straight line. Okay, let me zoom out a little bit. Okay, this formula is a linear equation because it makes a straight line. It intercepts the x-axis and it intercepts the y-axis. Okay.
Oh, I'm like vaguely starting to remember some of this from grade 10 mathematics. And I remember being god awful at it because I did not understand. Okay, so I had the same math teacher in grade 9 and grade 10, and I could not understand what she was saying. Like the way she explained things just did not compute with my understanding of life, I guess. And so for 2 years, I just struggled really bad. Like I went to her for additional help after classes to ask her to explain to me things in a different way because I didn't understand the way she was saying it, and she was incapable. Like she couldn't explain it.
And I hear that a lot actually. And what I think happens is a lot of people, when they're learning this stuff, they don't explain it very well. And so this is one of the reasons why I want to explain it graphically what we're doing before we try to do it analytically. Okay?
Because I remember this being it before we did slopes.
Mm-hmm.
So that's the... Oops.
Slope is your rise over run, right? So the m on mx plus x for your linear equation is your slope. So if you're familiar with that, this equation you at least should be recognized as a linear equation. It forms a line, right?
Right.
Okay. Now, I've said before, for any linear system, when you have two equations or more, there's only going to be a possibility of having one solution, infinite number of solutions, or no solutions. Okay. And so I want to explain what we're doing here and why that's the case. Visually, once you see it, you'll be like, oh, okay, this is why the case. So let me give an example of an infinite number of solutions to this system here. Okay, I just typed in the same equation, right? So at every point on this line is a solution. They're going to be the same solution. So there's an infinite number of solutions to be had here, right? I mean, if any point's going to match from one thing to the other, the same equation, right? But we're going to be looking for a system that has only one solution, means it intersects at only one point. There are other solutions, systems that are non-consistent. For example, like, let me put it a little higher. Like here you have two parallel lines, right? There's no solution to be had here. They do not intersect anywhere, right? This is called an inconsistent linear system. Okay, so this would be an example of a solution set that there isn't any solution to be had here. They don't intersect anywhere. In order to have these two linear equations to be consistent, they must intersect at least one place. And what we're going to be doing is finding a system where, oops, dang it. These are the two equations that I came up with. Equals 7. Oops.
What I recall being an issue when I was learning this in grade 10 and 11 is that they never explained where this applied or why you would use it.
Well, you'd use it when you have you'll use it when mostly like with transformations. Like if I'm doing a transform in 3D space, a vector space, then you'll be using matrix theory, especially because you're changing the x-axis, the y-axis, the z, and you're doing transforms. So when you're using with vectors and either in scalar quantities on a 2x2 matrix, you'll be using a lot of matrix theory. And so this will all apply when it comes to a lot of physics stuff.
Oh, okay. So this applies for if you're working in the field of physics and you're trying to work at maybe in engineering also.
Absolutely in engineering, yes.
You're building something and how the physics will apply. So if you turn something, how is that going to change within 3D space? And these calculations will tell you exactly if you turn it here, it'll be here.
Correct. Yeah, those are called linear transformations. All right, so this is my system. This is a consistent system. I made sure it's consistent, that there's exactly one solution. Because again, either an infinite number of solutions, one solution, or no solutions. So here we have a system where it intersects at one point, right? Can you see this?
Yes.
Okay, that one point that intersects will automatically give you the answer. So x equals 2, y equals 3. So graphically, we've already solved this system.
Right, because like this way and this way.
Yeah.
So where is it on the graph here, and where is it on the graph here on that x-axis and that y-axis?
Well, put it in there. Put like the second equation is a little bit easier. So if x equals 2, then 2 times 2 is 4, plus 3, 4 plus 3 is 7. Hey, that works, right?
Right. Yeah. So you can plot essentially what you've got is a program where you can plot the equation in, find the intersecting point, and that gives you your x and your y axis and your x and y variable.
Your variables, right? It doesn't give you your axis, but it gives you your variables.
Sorry, yeah.
Okay.
Yeah.
Perfect. And that's exactly. So this is a solution. This is the only solution to this consistent system of linear equations using two variables. But this is how simple it gets using graphics. Okay. So this is what we're trying to do analytically, and I'm going to show you how to do it analytically using very simple back substitution. But then we're going to solve it using matrix theory, using Cramer's rule. Okay.
So this is probably the easiest way to do it if you have essentially a graphing calculator.
Yes, for that very kind of simple system. Okay. Not all systems.
Okay, and
simple.
so we're going to up the complexity, and in upping the complexity, we have to start solving the equation using different formats.
Correct. Because once you get into very, you start getting into like high level maths, the complexity becomes real quick that you're not going to be able to just do it graphically like that. Especially when you're using three linear systems, there may not be a solution. So,
see, I'm not the dumbest of the dumb. Where's my $20?
Well, hey, look, if you could figure this out, I'll find somebody dumber. I'll find a 61 IQer to come in and try to.
Somebody was offering $20 for a demonstration of me ever saying anything intelligent. I feel like me explaining and figuring out that this works is me saying something intelligent, because my immediate response was, "Well, am I allowed to play? Give me my $20, bitch!"
Yeah, no, I think that qualifies. All right, so let's kind of do this analytically.
What was the name of the program you were using? Because I think that would be useful. Desmos?
Yes, Desmos.
Let me just Google search it and put it in chat. Desmos? Oh, Desmos graph. Yeah. Oh, ooh. Here you guys go if you guys are interested. This is the program that was being used. So if you are in a math class, or if you are in college and need something like this and don't want to buy a graphic calculator, here you go. Save you $60.
The problem is you're not going to be able to use it in class. But let me show some people on the real quick on the Desmos.
You'll be able to use it in class. You just won't be able to use it on exams.
If you look in the outside real quick, and you look at the Desmos again, let me show you what a quick linear transform would be.
All classes are at home right now anyway.
That's true, actually.
Steve doesn't know what he's talking about.
Yeah, that's true. So I just made an equation, very simple equation, right? But if I do a linear transform, let's say I want to times everything by 2. So I have 2x times 2 is 4, 4y, and then 40. This would be what's called a transformation. Okay, I've just changed the position of the line. Matter of fact, let me put the original before. Okay. So 2x plus y plus equals 40, and then I'm gonna do a linear transformation where I just basically multiply everything by the same amount. When you're doing matrix you're doing what's called row column substitutions, multiplication. You're changing things to transform it in order to find the coefficients of the linear equations. That's what you're trying to solve here, x and y. You're trying to find the x and y values by knowing the coefficients. So let's say I do a linear transform here, and so I times each thing by 4. Or it's by 2. Let's by 2x. So just 2. So let me go back up here, because 10, and so 20. So
you have to forgive me a little bit. I'm also seeing it when you guys are seeing it, so I'm also on the visual delay.
Yeah, she's not looking at the outside chat. So these two equations, they don't tell you anything new, right? Because it's not giving you anything that you can work with. All I've done is I've taken one linear equation and I've times it by 2, and I get the same thing. So it doesn't change anything. It puts it in the same exact spot. Matter of fact, when you're dealing with matrices, you eventually learn what's called ranks of the matrix, and the rank of the matrix is basically how many independent lines that you have of row or columns that you can use that give you new information, basically. But if I actually didn't want to do a transformation where it actually changes the position, right? Now I have 2 lines. Now I have a transform. Now I have a line that has gone from here to move to somewhere else. And if I start messing with the variable coefficients, then I start getting rotation across the x and y axis. Okay, these would be transforms in a 2-dimensional plane, y or x, right? So that's what we mean by a transformation, where something's rotating on the x-axis, the y-axis, and you end up with a different line that's still going to meet at one place, right? It still meets here, right?
Okay,
so there's still a solution to be
so-
had. It's a consistent system. If they were parallel lines, it's an inconsistent system, and there's no solution.
So it's right now it's rotating on the axis.
It's rotating on that point.
That's the transformation you're talking about. Is it's changing the angle on this axis in particular.
Yeah. Imagine having a photograph, right? If I have a photograph and I change it, I have it on the y-axis, and I rotate it with respect to the y-axis, you can actually see the image get smaller and smaller till it actually disappears, right?
Right. Yeah, because you're changing the angle until you're looking at it straight on as a piece of paper.
And when you have the slope that's zero,
space.
when you have it like just like this, it has disappeared. It has become undefined because it's divided by 0 at that point, basically.
Right.
Okay, because you're no longer even you're not looking at anything. You're looking at edgewise, which has 0 dimensions, right? And same thing with the x-axis. So those are why we would have linear transforms like that.
Right, because it could rotate this way, or it could rotate like this way, or it could rotate like, because you're working once you jump into 3D space, which is why you're going to go from 2 variables to 3 variables, right? Because you're adding.
Yeah, on the z-axis, right?
Right.
Because in 3D vector space, you're going to have the x-axis, your y-axis, and you have your z-axis. And that's if you think about it, for any kind of tensor equation where you have the three vectors, let's say you have a particle that has 6 degrees of freedom. And 6 degrees of freedom means that you can rotate on the x like this, you can rotate on the y, and you rotate on the z. And so a particle in free space can go any one of those directions, right? I mean, it can change with respect to the x, with the y, and the z. But if I know the coordinates, right? I know how high off the ground, I know how far, far from something, or the altitude, right? If I have 3 dimensions, I can have any position for any given particle. So I can use a 3x3 matrix to determine any vector, or it would be the scalar quantity, I guess.
Yeah, so now you've gone from two dimensions to 3 dimensions. Correct. And you can start with 1 dimension. You can start with like 3x equals 6. What does x equal?
Right, and that'd be x equals 2, and then you have a line there, right? Because that's a 1 dimension.
Right. And then you add the y-axis. So now you've got 2D, 2 dimensions. Then when you add z, you get 3. Now you're modeling in 3 dimensions.
Correct. Yep, that's exactly it. All right. So let's kind of solve this the old-fashioned way, which you would probably have learned in, I don't know, grade schools, 8th grade, 9th, whatever. So you want to find x and y. So one of the easiest way to do it is called back substitution, or at least I call it back substitution, where you actually rearrange to find, you want to isolate one variable and you want to put that equation into the other equation, right?
Oh, okay. So you've got the equation and you rearrange the equation back and forth until whatever variable you're trying to find is alone on one side of the equation, because then you just solve this equation.
Right. So if I rearrange for y here,
one variable at a time, except you're actually solving both at the same time.
Well, yeah, you're isolating one, but then because you can do that because they're equal, there's an equality there.
Right.
You can put that in the first equation. So if I isolate y on one side, it's real simple to do.
Like
right?
equation balancing.
Yeah. So what do I subtract on the second equation here on the set of linear equations? What do I subtract from both sides to isolate x? Isolate y. I just subtract 2x from both sides.
Right. So so it moves it to the other side, because if you subtract 2x from where 2x exists, it removes it. But because you have to do it to both sides, there is now negative, or subtract 2x on the other side of the equation.
Exactly. So 2x minus 2x is 0, so that cancels out. And then I'm left with 2x minus 2x on the other side. So my equation now becomes y equals 7 minus 2x. Now, because this is the quantity here, I could back substitute into the original formula, right? Because this equality, this 7 minus 2x, is equal to y here. And so I just take this and I stick it back into here, right? And I get this new equation.
See, this is why I think you should be writing it down as you go.
Yeah, you're probably right. Eventually I get a tablet.
I think it's a lot more clear. Maybe that's just me, though.
And then you just factor this out. So this is called distribution of multiplication over subtraction is the technical name for this.
Because you took the y equals 7 minus 2x. The next line there is you putting that into the first equation in the 2 that are above.
Right. Yeah. It's not that I'm dependent on all those. What it is I do each step by step, because what I really hate when I'm reading something in mathematics is when they just jump steps.
Show your work.
Yeah, I mean, you can do it, and when you get to college level, and you usually do, you don't show every little detail. But when I do these presentations, I try to do it every single solitary step so people know. But you don't actually do that when you actually take these courses. You generally don't.
Because y equals 7 minus 2x, then that next equation down, which is the first equation in the ones listed above, which is the 3x plus 4, y, you've replaced y with 7 minus 2x because we've segregated y or isolated y onto its own, so we know that 7 minus 2x is equal to y because we've balanced the equation the other way.
As long as you're balancing, well, as I said before in the hangout that I did with the Google, college algebra. Most of college algebra is basically the same concepts: simplification, combining like terms, balancing the equation, factoring. These are concepts that are used ubiquitously throughout mathematics and especially college algebra. All right, so once you distribute this, again, multiplication over subtraction, you end up with this formula here, and then you combine like terms, right? Well, what are I have like terms here of 8x and 3x, right? X is the term. 3 and 8, negative 8 are the coefficients, so I can combine them, which gives me negative 5x, correct?
Right, because we need to do the equation in specific order.
Yep. And then I combine the constants. Okay, these are non-variables. So I just combine those. So I subtract 28 from both sides, which leaves me negative 10 on this side, correct? 18 minus 28.
Mm-hmm.
Okay. And then how do you solve it? How do I go from minus 5x to negative 10? How do I find x for that? What do I divide by both sides with?
2.
No. If I have negative 5x, what do I want to divide it with to get rid of the negative 5? Anything over itself cancels out, right? So negative 5x over negative 5x is just x.
So you would just remove, so you would just take negative 5x and you would do negative 5, you would do negative 5x over negative 5 and put negative 10 over negative 5. And so you would get negative 10 divided by negative 5 equals.
Perfect. Exactly. That's exactly what you're doing. Because when you're subtracting negative 5 on both sides, you're actually just basically saying negative 5 over negative 5, 1.
I can do that.
And so
too.
negative 5 over negative 5 cancels each other out, right? But it doesn't cancel on the other side, so you're left with negative 10 over negative 5. So
that's
one way of looking at it. Like I said, when you're dealing with math, I mean,
you're isolating.
You're isolating, yeah.
Yeah, so you're doing you're doing the portions of the equation. Okay, so I have a question. Is it possible to isolate x without doing some of this equation? Like, do I need to do 7 minus 2x multiplied by 4, or can I balance the equation to isolate x?
No, you have to stick that quantity in for y.
I have to because
you're
there's 2 x's, right?
Yeah. Because you see y is equal to this, right? So this y is equal to this quantity, and in the first formula I know it's 4y, so I can get rid of the y and I can just put that quantity that I know in. So that's exactly what you're doing. So when I end up with minusing or just dividing each side by negative 5, I end up with x equals 2. So now I know one about the variables. Now think about this: I have 2 variables in an equation, and I know one of them, which means you should be able to say, oh, well, I can definitely rearrange the formula to find the unknown, right? Right?
Right.
But we've already done that. We did that initially, right? With the y. We figured out, okay, y is equal to this. So now I have the variable. Yeah,
now that you know what 2 is, you can put, or now that you know that x is 2, you can go back to the other equation of y equals 7 minus 2x and put 2 in place of x because we know that x is equal to 2.
Correct. Yep.
So now you've got 7 minus 2 multiplied by 2.
Yep. And then you
just 7 minus 4.
End up with y equals 3.
Yep. Y equals 3.
And that is the solution. Which, by the way, remember from the graphic, remember the point that the lines intersected?
Yep.
So that's why I said graphically it makes a lot of sense. You go, okay, I want to figure out the solution to the set. And again, x and y have to be such there's only one solution set, or none, or an infinite. There's no other options for a linear equation. Okay? But to be a consistent set of linear equations, it has to have one solution here. Okay? By the way, somebody asking for calculus videos. I'm gonna put I have a playlist.
We're getting there.
Yeah, I have a playlist. I actually did Calc 1 and Calc 2. I did like 5 or 6 different videos on Taylor series and some other stuff. So if you want to go check those out. All right. So now we're going to actually do the same thing using matrix theory.
I'm going to graduate college math by being the dummy in the room.
All right. So now we have matrix theory. This is going to be fun.
Okay.
Right. So what a matrix is basically an array, right? It is, if you ever done anything with computers, when you're working with arrays and you like do what's called dimensions, you're actually setting up something in memory to say, I'm allocating these memory slots to put something in. So if I want to say I have a 2x2 matrix, I'm setting it up so I can say this. If I want to point to this location, give me the value out of it. If I want to point to this location, give me the value out of it. So the way we do this is called indices, okay? Or index, you can call me the ones. But these indices, usually it's set up for a 2x2 matrix, meaning I have 2 rows, right? One above the other, and 2 columns, one side by side. So there's a couple of ways you'll see these, but one of the easiest ways is basically you just say one is your location, 1 2, which means first row, first column, first row, second column. A2 1 would be second row, first column. A2 2 would be second row, second column. Okay. So just point to a location.
It's a grid.
It's like a grid. Yeah, it's an array.
1 2 3. It's like a box. In this case, it's a box.
It's a box
because you've got 1 and 2 and 1 and 2.
Now, these types of matrices, if you kind of extend it out almost infinity, you end up with basically what's called MN array or MN matrix, where M is your rows, N is your columns. So an MN matrix is where the M equals rows, N equals column, and M and M must be positive integers. In other words, you can't have a negative row, right? You have to have, you have to have a positive integer to have a matrix. You have to have at least one row or at least one column, or some combination of them, right? You can have a whole column, you can have a whole row. It doesn't matter. As long as you have positive integers, you can set up a matrix. Okay. Okay.
So you can have one column and one row, which would be what would that look like? That would be
okay.
Like
one row. Well, one row means that you have something going across this way.
Across, okay. Yeah. So this would be
one. But if you have one row,
rows.
You automatically have you have one row and no columns would just be like 5, 6.
This is
A. Those are because you remember a row is going across and a column is going down. So if I have A,
right.
B, or 1 5, that is one row, but it also has 2 columns.
So it's a bingo card.
Well, you think of it as basically, if you see numbers going across this way, that's going to be your row. Uh-huh. If you see numbers going down this way, vertical, those are columns. Okay, so in this yeah, as a matter of fact, Battleship is an array, right? I mean, B5 is your index to where that location is, right?
Yeah.
So in this matrix here, I have one row, another row, and I have one column, another column. So I have 2 rows and 2 columns. We call that a 2x2 square matrix.
Gotcha.
It's square because 2x2, right? And we'll check 62's IQ here. If a 2x2 matrix is a square matrix, what do you think they might call a 2x3 matrix? That's not actually square, but it's still
a rectangle.
It's still a parallelogram. It's a rectangle. It's a rectangle matrix.
Hey.
So, yeah. And there's also identity matrix, and there's also inverse matrices.
All rectangles are parallelograms, but not all squares are rectangles. Something like that.
All squares are all rectangles are square. Or sorry, all squares are rectangles, but not all rectangles are squares.
Right. All right. But all of them are parallelograms.
All of them parallelograms because they have 4 sides. All right, yeah, we're going back some geometry here. All right, so what we're actually doing is saying that this is a real matrix. These are not complex numbers, right? So when you have an indices, generally what you'll be using is I and J to figure out the location. So if J would be I would be the row and J would be the column, and they are this little symbol here that means element of. R means the set of real numbers. And then MN means that's the matrix, M times N. So this is saying that all these matrices that we're going to be using, our elements, are going to be part of the real number system. Okay.
Okay.
The reals, not the complex plane.
There's a symbol underneath A in the equation. What was that symbol?
This symbol right here is actually IJ. It's really hard to read.
Yeah, it's a little bit. Okay,
Yeah.
so that means and IJ is the rows and columns.
Yeah, it's really hard to read this, but this actually says IJ right there. So AIJ, because that's going to be how you're generally going to see it written.
Right. So there's the A in the brackets that has the symbol there that's supposed to say IJ. It's just hard to read, and that's rows and columns.
Yes. I is your row,
and
J is your
then
column.
You said E is the element of
this symbol here, this epsilon-looking symbol. That means element of R, and R is your set of all real numbers. So if it was epsilon C, was called double strike or bold strike, just double strike R. If it's double strike C, means it's going to be element of the complex numbers. Okay, all the reals are elements of complex, but not all. But complex are not an element of the reals. So, for example, like 2 is a complex number. It's a real number and it's also a complex number. Okay. But 2I is a complex number, but it's not a real number. So reals are a subset of the complex, and it really confuses people in that when they say, "Well, how is 2 a complex number?" It is. Because basically, if you think about a complex number, right, it is the formula of AI plus. But I know this has nothing to do with what we're talking about, but it's math. AI plus B is right. So AI is your complex part of it, and your B is your real part of it. But if I have no imaginary part, right? If AI equals 0, if A equals 0, that part goes away. I'm just left with B, the real part. That's still a complex number, right? So it just doesn't have an imaginary component.
Okay.
Does it make sense? So all real numbers, 5 is basically AI plus 5, where A equals 0. That is a complex number.
Okay.
Okay. So like I said, a lot of people get confused by that. They don't understand why real numbers are complex numbers, but they are. All right.
Well, by that, wouldn't all real numbers have to be complex numbers also?
That's why reals are. I get it. 62 IQ gets it. The real domain is a subset of the complex domain.
Yeah. Got it. Okay.
All right.
All real numbers are just complex numbers where A equals 0.
But A equals 0 on the AI plus B. Yeah.
Yes.
She gets it, man. Holy crap. Canadian education is still better than America. Holy crap. Even if she's 11th grade. By the way, let me ask the outside chat. I haven't been paying too much attention
saying
to
that I only graduated grade 11 now.
Yeah.
That I only did school to grade 11 because of so in Canada, you only need 3 math credits.
That's it? Really?
You only need 3 math credits to graduate, but you are required to take grade 9, grade 10, and a grade 11 math. So you can take more maths, but you can graduate by only taking those 3 that you're required to take. So I only took the 3 required, not including I did a lot of tech. So I did like woodworking, shop, metal, like I did so there was mathematics in those, but they counted as a different kind of credit.
So let me ask the live chat. Are you guys following along real quick?
They look like they're following along.
Yeah, okay. So what we're going to be doing is, when we're doing these linear equations, again, we're looking for the variables given the coefficients. And so most of the time, you can set it up different ways. I set it up this way. Okay. Again,
I'm going to be so hungry after
this is personal preference only. You read about different ways. Sometimes you'll see it written AX plus BX equals C. That's fine. And you'll say it'll be like A1X plus B1Y equals C1, and then you would have A2X B2. I mean, so that's fine. Those are your indices. Again, doesn't really matter what the indices are. We're going to be using it this way by saying that A is your coefficient, X is your variable, B is your coefficient, Y is your variable, and E. And now,
okay, I want to make sure I understand this real quick. X and Y are still variables as they were before.
Yes.
Right? A and B are now representative of
constants.
The location. Yeah, the location on the grid we talked about.
No, not what it is. Okay. The higher letters, this is something I probably should explain. The higher letters, X, Y, and Z, are variables. This is by convention. The lower ones, A, B, and C, are constants. So AX, when you see AX in college algebra.
Oh, okay. So like if I was looking at an equation and it told me that 12x plus 4y equals a number, the 12 is in this case would be A, and the 4 would be B.
Bingo.
So So because we don't have any constant numbers to input into the equation yet, that's what the equation looks like before you have what any of those constant numbers would be, and we don't know what the variables are.
That's exactly it. This is the format.
Okay.
Right, exactly. So ax plus b equals e is basically saying, okay, what am I supposed to stick in here? And you go back to your original thing, right? A would be 3x plus 4y. 4 would be b, and then c would be your 18 here, right?
So this is essentially the equation that we solved. You could input the equation that we solved before in there, but with so A is 3 and B is 4 and E is 18.
Correct.
Okay.
Yeah, and the reason why you set it up this way will make sense here in a second when you start doing the actual the 2x2 matrix. Okay, so a matrix, generally matrices are represented by capital letters. Okay, so A equals B equals, and I'm just using M. So M is a matrix, represents a set of any matrix where AB over CD, where A and B are one row, C and D are another row, AC is a column, BD is a column. So basically A, B, C, D, right?
I understand.
All right, so that's real simple, right? To set up the 2x2 matrix here.
Got it.
But we're going to plug and chug the numbers
two columns, 2 rows.
2x2, right? Because if you look at the original equation here, I have 2 variables and 2 equations. I want to be able to solve them, so I have to set it up. And we'll show you how to set it up here. I'll show you how to set it up. But stick in the numbers here. So A, B, C, and D. These are the coefficients, right? A and B were 3 and 4, right? 3x plus 4y. And C and D on the second equation, right, would be the coefficient. And what's the coefficient here for y? You don't see it, but it exists.
Okay.
1.
So okay.
Because this is actually saying the same thing as 2x plus 1y equals 7, right? But you just don't show the 1, right? But it's the same thing. 1y and y are equal to each other.
Yeah. The one is
right
there, but it doesn't matter because it's 1 multiplied by whatever the number is, so it's going to be whatever the number is anyway. So you just don't even bother putting it in the equation.
You don't need to see it.
From like a really long time ago.
It's not explicitly shown, but it's implied. But it's so funny because every variable that doesn't have a coefficient has an applied coefficient of 1. It's just that's how it works in math. All right. So now that we have the actual matrix here, we have a 2x2 matrix, right? Using the coefficients. Good so far?
Yes.
All right. Now we have to find what's called the determinant of the matrix. And the determinant of the matrix is a kind of a special number that exists. It's a very specific, unique number that you can be using later on to solve the system. And you'll see it looks at you'll see it as DETA, determinant A. You'll see it as A with absolute value bars sometimes. And the way you actually solve it is basically you do what's called a cross on it. You'll say define a determinant. You'll take 3 times 1 minus 4 times 3. So what you're going to be doing is you're
cross multiplication.
It's going to be a cross like this. So what you end up with is AD minus BC. Now, why these are like this, and when we get into Cramer's rule, why it works, there is a way to derive it using an algorithm, using mathematics. I could probably explain it another time, but it's beyond the scope of why this actually works right now. But just go with it. It's one of those things that, like I remember in nuke school, they would tell you, look, you're not going to understand this right now. Go with it. We'll explain it later on somewhere down the line. Same thing in college, too. They do the same thing. Right?
We'll get there.
Yeah. All right. So this is what we're looking for. AD minus BC to find the determinant. Okay. So you're also maybe seeing it written like this, again, with the different indices. A1x plus B1y equals C1. You'll see that a lot, especially in college algebra, because when you're doing polynomials, you have to do expansions. And so you'll see like A1 plus B, A1 plus 1 plus, x. So you'll see it expanded out. So you might see it in this notation as well. Again, don't let the notation confuse you. Think of the concepts, right? These are saying the same thing.
Right.
All right, so the determinant of A is going to be AB over CD, which we've already established. So AD minus BC would stick in the numbers, right? And
okay. So yeah, you're just
plug and chug. It's called
adjusting. Yeah, you're adjusting the equation to. Yeah.
Yeah. So AD, right? We go back to here. Remember, these are my coefficients.
Yeah, you're cross multiplying. So
you're cross multiplying. Where you're not really cross multiplying. What you're doing is you're taking basically a cross of the matrix. And again, why it works this way, I'm not going to get into.
Well, okay.
But you got this is the algorithm that you're using. Okay. Oops. Let me go back up here. So I'm just saying AD minus BC. You just have to remember, that's all you have to remember is that you're just taking this diagonal and you're subtracting that diagonal the opposite way.
Right.
Okay. So now that I stick in the coefficients here, A equals 3, D equals 1, because remember, right? 1y, minus 4, which is B, and 2 was your C, right? Because those are the coefficients that we had. And again, going back up to here, these are what we're dealing with, A, B, C, and D. Right, so 3 is A, 4 is B, 2 is C, 1 is D. That's why I did this way for A, B, C, and D. So you can actually see it that way.
Right.
All right, so
AD minus BC. Then you plug in the numbers, and we're just using the numbers from the equation above.
That's it. You're just taking the coefficients. So what is my coefficients? Well, 3, 1, 4, and 2 are my coefficients. The first equation, 3 and 4. Second one are 2 and 1. Those are my coefficients.
And we figured out what x and y were, so you can plug those in.
Yep. So what is 3 minus 5 is negative 5. Right? So my determinant is negative 5. Now,
3 minus 8.
What's that?
3 minus 8 is negative 5.
Yeah, 3 minus 8 is negative 5. And so I'm just going to rewrite determinant A as D. Because when you're using Cramer's rule, you don't have to write A, you just use D. Okay, so D is my determinant. This is my special. Negative 5 is the determinant for this set of equations. Okay? Now comes the fun part. Now we want to use that information to actually solve for X and Y.
Yeah, so that's what I was wondering. Okay, so this is going to get us to a point, and how are we going to use the negative 5?
Correct.
Let's find out, boys and girls.
Yes, the negative 5 comes into play here real soon. Okay. So what I wanted to do is I would set up what's called an augmented matrix. Okay, so you have different types of matrices. Like I said, you have the coefficient matrix. You can have a variable matrix. You can have a coefficient matrix. And when you start using transforms and you start actually manipulating using inverse matrices, you'll be using augmented all the time because you use row column manipulations. So an augmented matrix is basically my coefficient matrix with my solution, or not solution. I guess the EF is basically your whatever these things are equal to.
Or whatever equal to.
18 to 7. Yeah, it's your augmented matrix. Okay, so
18 and 7.
So basically, I use a little bar here. You'll see that very frequently, a horizontal bar.
Yeah. Okay, you're using that to determine.
Yeah, to separate these because
separating the other side of the equation.
Correct. This is showing you that this is my what it equals, right? The augmented matrix, and this is your coefficient matrix. Okay, and so when I stick in the numbers, I end up with 3, 4, 18, 2, 1, and 7. Right?
Got it.
Right. I mean that right there should make perfect sense to you right now. Right?
Yes.
Because 3 is the.
I understand this.
All right. So let me do a quick test. So 4 is the coefficient to what variable and what equation?
B.
B. Okay, which is the first equation for the y variable.
Multiplied by y.
Okay. Yep, she's got it. See, quick check. She gets it. All right.
Yeah. So I want to see if I get this right. So if I were to rewrite that with as the equation, it would be 3 multiplied by 1 subtracted by 4 multiplied by 2.
Perfect. That's it. That's how you define the determinant. Right. Exactly.
Okay.
So now we're going to be using Cramer's rule. This is where the determinant comes in handy. And as Pio Chanel says, he says it's basically like a key. It is. It's kind of like a key to solving this stuff. You find the determinants, you can find the keys. So we're going to find multiple determinants. There's a main determinant, which is of your matrix, and there's a determinant for the x and for the determinant for the y. Then we're going to use it as a ratio to figure out what x and y actually are. All right. So Cramer's rule states this. X equals dx, which is your determinant for the x, over d, which is we already know is negative 5. Okay. Y equals determinant of y over D, which is -5, where D does not equal 0. And why do we want D not equal to 0? What happens when D equals 0 here?
That's when you get two parallel lines that don't intersect.
Or no, worse. What happens when you have something over 0?
Oh.
The universe explodes and everybody dies, right? You don't want to have division by 0 in this type of math. Now,
Todd asked, are these also known as systems of equations?
Yes. This is a linear system of equation, right? The two linear equations I gave is called a system. It's called a coherent, a consistent system, because there's one solution to be had. If there's no solutions, it's called an inconsistent system. But yes, this is a system of equations. Yes.
I'm gonna have to
two
ask
equation,
Chat.
two variable system.
I'm gonna have to ask Chat to do me a favor and keep track of how many times I'm able to understand, figure something out, and rephrase or actually succeed in doing the equation. Please keep a tally of how many times I'm able to do that, and then whatever that number is, multiply it by 20. Because that's how much money I'm going to get for this stream.
Yeah, I'm telling you, for a simpleton, I'm impressed. I'm not even going to lie. Because I got a lot of detractors, and I guarantee probably 95% of them wouldn't know what the hell is going on right now. They just wouldn't have a clue. I could explain it to them blue in the face, and they would still never get this. For $1 million, would they be able to explain it? So, and I'm not even joking. That's not hyperbole. There are some people out there that are just so unable to do this kind of stuff, yet think that I'm an idiot for some reason, right? Okay. All right, so again, why this works, Chesh, go with it, okay? I will do another video if I have to explain how to derive Cramer's rule. I can do that, but it's going to a little bit more involved, and I'm not going to do it right now. But to figure out the determinant for the x, right, the x variable, is going to be taking the EB over the matrix, 2x2 matrix EB.
That's American, by the way. So I'm gonna get that in American money, which is the exchange rate for Canadian. Just saying.
So basically, what I'm doing is I'm taking the augmented matrix here, EF, right? Because 18 and 7, and BD, which is going to be your column here. So I'm taking the augmented matrix, 18 over 7, and the BD column here, and I'm putting them into a matrix. Now, that's going to give you, when you cross multiply or cross, like I said, so that's going to give you ED minus BF, right?
Right.
Okay. Now figure out the Y is a little bit different. Figuring out the Y, and again, why this works this way, not going to get into, just go with it, is I take the AE and CF. So basically AC, which is your first column here, and then your augmented column here. So
okay, so you're taking, I want to make sure I understand properly. You're taking the two equations and putting two equations into two more equations that are matrixed.
Yeah, but think of it, the easiest way to think about this is in the first matrix, in the matrix here, the 2x2 matrix, EF is basically your augmented, and then BD is your your second column. And then to figure out the other one, it's your first column times with your augmented. Okay, and again, why this works this way, complicated.
It is.
But just go with it. That's how you do it. All right.
All
right. So if for figuring out dy, if my matrix is a 2x2 square matrix of AE and CF, what would you expect me to do to cross?
AF and EC.
Yeah, AF minus EC, right.
Yeah.
Perfect. All right. Okay. So now I know how to determine what my dx, or my determinant for x is, and dy, my determinant for y. Okay. So I'm going to plug.
We already know that the determinant is -5.
My determinant is -5. So I've already got the denominator. What I'm really looking for is the numerator here, right? Because if x, it's a variable
you're
x.
looking to try and figure out what x and y are.
Yeah, because if I already know, because of Cramer's rule, that x is going to be equal to the determinant of the x matrix over determinant of the initial matrix I'm working with for linear equations, then I know that if I solve the dx matrix and I put it over -5, it'll give me the variable out of it, right?
Okay.
And by the way, there's multiple ways of solving this. You can use inverse matrices to solve these as well, which is a lot more complicated, and I'll do that in another video.
So I want to make sure, 'cause when you're doing this, I assume once you've learned it, you're not starting off by writing out the matrix every time. You're just starting with, you've got the equation, and then you just flip it over into this equation and you just plug your numbers in.
Right.
So the A, B, F, E won't actually be there
Yeah,
because
once
already
you
know
start
that
doing
those
these,
things are
you do them, and you just do them on
you're
paper.
punching.
Right.
Yeah, because you're just punching the numbers in.
Matter
Because
of
we
fact, I'm glad
already
you brought that
have
up.
the initial equations.
Right, I'm glad you brought that up because I do actually show at the very end a shortcut.
Perfect.
And that's what your homework is going to be. By the way, I should probably tell my lobby audience, there's a homework assignment to be had. You have 24 hours to do it. Show your work on Twitter. You should be able to figure it out. My only issue is I don't know how you're going to like do it unless you handwrite it out and then take a picture of it, or you put it in Libra Math. Okay, but we'll see if you guys can figure it out. So there's a quiz at the end, but you have 24 hours to figure it out. And I will call out who actually solved it right.
And we'll be going over that on Caffeine Corner because I have to do it too.
Yep. Actually, it's a little less than 24 hours. All right. So here's my matrix for figuring out
tomorrow.
For tomorrow. For dx, this is my matrix, and so ed minus bf. Now just plug and chug. I stick in my coefficients, my augmented, right? So 8, 4, and my column BD. So 7 was for B and 1 for D, right? So is that right?
It's easier I should have taken notes. I can't scroll, so I can't see it.
Oh yeah, because I'm scrolling through here. Yeah. Right, B. I'm just looking here. Where I got the B from? B. No, I made a boo-boo here. Where did I make a boo-boo?
Y is 1. 4 is B. You've got 4 in F.
Yeah. I have 4 in F.
I think you just plugged in. I think you just plugged the number.
I see. Yeah. This should be. I can change this on the fly. So it should be 18 and 7, and then 4 over 1.
Why would you don't do this while holding a pen? Just open up Notepad and key in numbers. Don't do it with a pen.
There we go. I just plugged and chugged wrong. Okay.
Yeah. You just, one of your. Oh, okay. Yeah. Sorry, I'm still behind on the screen.
Yeah, no, I'm fixing it
right now.
I just plugged and chugged wrong.
Does it count that I figured out what the error was?
Yes, it counts.
Does that count? That's another $20. Pay me.
All right. So it's going to be 18 times 1 minus 4 times 7. Okay. You rearrange. You move it around. You end up with dx over equals -10. Okay. Hopefully I got that right. Did I get that right? Because it's again I plugged and chugged wrong, but I already did the math. So you should.
I can't tell if you're right or wrong right now because I'm still catching up.
Yeah, I don't want to
I wouldn't trust me anyway.
The problem is I'm working in math lab and it's a little bit, or not math lab, Libra Math, and so it's a little hard to manipulate some of the stuff on the fly. But you end up with dx equals -10, and x equals dx over d, right? So what is x equals -10 over -5? X equals 2, which would we expect, right? Because we already knew that it was 2 from 3.
We already know that x equal 2 because 1, we did the graph, and 2, we did the other way of doing the equation.
Correct.
We did the balancing act.
Yeah. I'm just going to take this line out here because it sucks. So I'll get rid of that. So,
okay.
Yeah, we just solved it that way.
And so, okay, so hold on. I need to catch up for a second.
Go ahead.
So we got to x equal 2 because we knew that d equaled -5, and so I'm how do we plug in? How do we get to -10 there?
Because 18 minus 28 is -10. 18 minus 28.
Okay. Got it.
I mean,
that's how we got the -10,
like
and then it was just the -5.
There we go. Does that help you?
On one equation and one on the other side, and then we did the exact same thing before, where we just said, well, -5 and -5, and so we got the 2. Okay,
yeah,
I got it.
Yeah, because 18 times 1 is 18, minus 7 times 4 is 28. 18 minus 28 is -10. So what confused people is I plug and chug the wrong thing here. But here's the thing about math: it's objective. It's easy to figure out when you make your mistake. You're like, oh shit. Okay, yeah.
Well, it's taking me a second. I'm gonna have to repeat some things just because, again, I am seeing it when you guys are seeing it.
Yeah.
So I'm a little bit behind on. So Steve's saying something, and then a minute later, I'm seeing what he was saying a minute ago.
Yeah, I'll try to advance it before I start going into it.
That's
but we saw how we solved for 2, right? We figured out the determinant,
yes.
and then we figured out the determinant for the dx, right? But using a different the way of taking the augmented and the column. Yeah. Now we're going to figure out dy.
Same thing, different variable.
Same thing, different matrix structure, right? So with dy,
well, yeah, the structure is different because we're trying to find the y variable, not the x variable. Right? Because in the last equation, we were trying to find x, and now this equation, we're using a different augment because we're trying to find y instead of trying to find x. That's why they're different.
Correct. So in this type, yes, exactly. So the matrix for the dy is going to be AECF, okay? Okay. And again, why it is, it just is. But
right,
again,
yeah, so we've got AFEC, because you read the equation left to right. So E goes before the C because you're reading left to right.
Well, it's going to be because AF minus EC, right?
Right, but I'm just saying E has to go before C because that's the order the equation is in.
Well, yeah, well, actually, it's more, I want to think about that way. I know what you're saying, but don't think of that way. What it is AC is, in your original matrix, the augmented matrix, it's AC is your first column. And EF is your augmented column. So what you're basically doing is you're making a new matrix using your augmented column and the first column for Y. Now, on the DX, it was a little bit different, right? It was your first column, and then it was your augmented column. And again, why this is too much in depth to really go into, but that's what you're looking at. If you wait a second for it to catch up, this is what you're looking at here. You're looking at AC, which is your first column, first column, and then your augmented column, and that's how you make the matrix. So now you have AF minus EC, and then you just plug the numbers in. Okay, so I end up with 3 times 7 minus 18 times 2, which is going to be 21 minus 36. 20 minus 36 is negative 15, right? And since I knew that dy over d to figure out my variable, I end up with negative 15 over negative 5, which is y equals 3. Hey, what did we say from the very beginning was, even from the graph where they intersected, right, was yx equals 2, y equals 3, which now we've solved it 3 different ways. One was graphically, right? So that's not an analytical solution, but it shows us what we're looking for. We're looking at the point where they intersect, where I can get x and y, where the system of equations makes sense, right? Because if I put some numbers in there that don't make sense, they're never going to get to a point where they actually intersect, right? So I have to find a value for y and x. These are unique values, right? Unique values. There's only one solution here.
Because it can only intersect at one spot.
It can only intersect at one spot, right? So there's 3 different things possible. They intersect at one spot, they intersect at no spots, which means they're parallel, or they intersect at every spot, which means they're the same equation, right?
Which means they're same line, right?
Would be so. There are possible to have an infinite number of solutions to linear equations, right? All right, so let me give you the shortcut of way of doing this, and then we'll kind of like call it a day.
Pretty good. I think we're doing pretty good.
I think you're doing amazing. Look, I'm not just blowing smoke up your ass.
My brain was not on today either. I'm like, no, he's like, hey, do you want to do this thing? And I was like, no.
Oh yeah, no, I asked her. She's like, not really. I'm like, what are you doing?
No.
No, I'm not trying to be dismissive, but you're doing a hell of a lot better than I even thought you. I knew you do well, but you really are grasping it like that. So that's the
thanks.
For 62 IQ, simp. I'm telling you, I'm not bad.
It's because I'm wearing my glasses. I'm up to 63.
They do kind of enhance low. It's like +1. Yeah.
Yeah.
All right, so let's do a little shortcut. This is how you would normally do it, much quicker, right?
So I just want to figure out.
Yeah, I just want to figure out x. So I know it's dx over d, right?
Right.
And I know the matrix for dx is this, and I know the matrix for the determinant is this.
You've squashed the equation.
Yeah, I just put it into one thing. I just said, okay, my dx matrix is this, my determinant matrix is this. Now I just do the cross, right? So ED minus BF over AD minus C. And I just put the coefficients in the augmented thing. I just stick in the numbers, right? That's all I'm doing. And so I end up with 18 minus 28 over 3 minus 8, which is negative 10 over negative 5, x equals 2. Boom. I've just solved my variable just by doing that.
So, you've just taken the 2 steps and combined them into one big equation.
That's it. Now, again, you might see them written differently. You might see like A1, B1 over A2, B2. You might, again, the indices doesn't really matter what you're using. It's the concepts that we're going for here. Right?
Would that only matter if you weren't using a constant?
Well, no, these are all, the coefficients are always going to be constants, right? So the indices are your locations, the matrix, right? So when you use normally you use like AIJ. AIJ will give you your row and your column, but you can also use
the only reason I can imagine you would need to use A1, A2, A3 is if you're ending up with like the same number, or if
no, they're different numbers, right? A1 and A2 can be different numbers. A1 is your location, right? So A1 is here, A2 is here in the row. But you would normally use
it's the same column is what I mean. So when you're working if you're working on a large enough scale that you're dealing with like 3 or 4 or 5 columns, then you would want to indicate in your equation 1, 2, 3, and 4.
Yeah, it'd be A1. It would be okay.
Which column it is?
It'd be if you're in the same row, it'd be A11. The next one would be A12. Next one would be A13. Next one would be A14. Right? 1, 4 because one. Or just you put them together, it doesn't matter. But 1 is going to be your row and 4 is going to be your column. So this is why, again, the indices is just pointing to a location in your array. That's all it's doing.
Right.
All right. So, by the way, once you find x equals 2, you don't normally have to go do the dy because
you wouldn't need to because you now know what the variable is, and then you can do the balance and just solve the equation for y.
Correct. But here's your homework. And for the live chat, set up the shortcut here for dy, for figuring out the variable y. So what it would be, I'll start you off. It's y equals dy over d. Then give me the matrices you would use. Hint, the determinant is the same. The numerator is going to change. Then figure out your cross, and then plug and chug your numbers, and then show your work to get y. Okay? Think you could do that?
I'll try.
You know what I'm asking for, right? I mean, we've already did it up here.
I understand. Yeah, I understand the question. Okay.
Now let's ask the live chat. Live chat, do you understand what we're asking for here? Figure out the very short.
1 in the chat for yes, 2 in the chat for X in the chat for yes, Y in the chat for no.
I'm gonna put X here. Yeah, why? Like why? Why are we doing this? So Treefeagle says, but Steve, these are just incredibly simple formula. Try more complex one, and it's a nightmare to use. Well, of course, this is intro stuff. This is like Matrix 101 here. Wait, we're not going to get into the Gauss-Jordan back substitution methods or echelon stuff. Maybe later. But
I do have a question though. Why would you use one way of doing this equation over another way of doing the equation?
Because sometimes matrix is the only way you can actually solve it when you're dealing with complexities.
Okay, so is that because it's like too complex to do it and now is that because it's too complex, or it would just be too big to try and write it all down?
Both of the above. I mean, when you start dealing with linear equations, like it's so complicated, and you have so many of them, what matrix theory does is basically compactifies things. Now, you could do it the old-fashioned way with linear equations to solve these things, sure, if you really wanted to. But when you have multiple linear equations and you have to write it out by hand, and you have to do all these row column manipulations to get, so it's very, very difficult. Right. And sometimes with three systems, you can't always just back substitute it. So matrix theory is a very compact way of doing it, where you're not writing out these long equations all the time. It's just a simple way of simplifying it.
Faster because you're not spending all the time and then back and trying to back and forth each piece of the equation, which is ridiculously long. Now you've managed to condense it all into one place that makes it a lot easier, where you just plug the numbers in and then do the actual math.
Right, because it gets a lot more complicated, because there's sometimes you have to use what's called an inverse matrix to solve it. The matrix equation is actually ax plus b. Okay, that's your matrix equation. And so when you're doing an inverse matrix, it's a little bit hard to explain without actually showing you how to do an inverse matrix. But you can use the inverse matrix to determine the variables as well. There's also what's called echelon way of doing it, where you're trying to figure out by setting these things to 0, and you have a column of zeros in the first row, leading column of zeros, and then you try to get all zeros, and you have what's called you have a little triangular shape. Then you actually start trying to determine one variable, and then you can start putting that back into the equations to solve it, because sometimes it's, like I said, it's very difficult to solve these matrices. Cramer only works like this way for certain things, where there's only one solution, where you have a 2x2.
Is that the guy? Is that the name of the guy who figured it out?
Yeah.
So I have one more question. Do I get additional points for having, 1, done this on a stream, 2, had to deal with a lag issue with actually seeing the visuals, and 3, actually participating with and in live chat while doing it?
Yeah, I think the bonus plus. Yeah, this was by the way, his name was named Gabriel Cramer, and it was back in the early 1700s he came up with this. But again, when you start working with a Cramer rule for 3x3, it gets a lot more complicated. Again,
I'm already kind of starting to foresee where this goes when you add another axis, as soon as you add in 3 dimensions, where it's like, oh god, so now you'll have your x, y, z, and then your split off equals your e and f, right? Well, whatever letter.
Well, yeah, think about it, because okay, so again,
so you'll have 1, 2, 3, and then that line, and then 2.
Right, you have a 3x3 matrix, and then you have your augmented,
and then you have the augmented. Yeah.
And again,
foreseeing this, I can see how this gets complicated really fast, or how this expands and gets bigger.
Is a rank 2 matrix, is called a rank 2. But when you start getting into higher ranks, it gets a little confusing, because a rank is basically, it's not so much what you have, is you're getting any more information out of it. Again, if I just do a transform and I just times everything by 2, that's not a higher rank. So if I have three equations, but one is basically a transform of the other, that's just like multiplying by the same thing, it doesn't increase the rank. And so rank is determined on either your columns or your row. But they come out, from what I remember, they kind of come out the same. But you start dealing with rank, like 5. So
yes, you have a huge system here. You've got 5, and then you're augmented, right. So you end up with 6
with multiple variables of x, y, and z.
Right. So. Right. Yeah, no, I can definitely see where this is going. And awesome. I don't know if I'm comfortable with that.
Well, like I said, no, go when you get a chance, look up what's called Gauss-Jordan elimination. And this is what I had to learn. You just call it Gaussian elimination, but it's actually Gauss-Jordan. But I actually had to do that kind of math, and it sucked. I'm not even going to try to explain it one of these days, maybe, but it's very difficult because you're doing row column manipulations to get all zeros in your lower echelon, and you want this nice triangle type shape. But anyways, guys, thanks for watching this. Again, I like doing these math stuff. I'll probably do more throughout the week. They're not for the getting a lot of views, and I don't care.
This is not for the faint of heart.
I do these things because I enjoy it, and I want people to get something out of it. And if one person, just one person, like 62 Simp, gets something out of it, I feel like it's worth it, And by the way, you guys got to admit, she did exceptionally well. I mean, if
you guys could do me a favor and count the times that I was intelligent and figured it out and was able to rephrase it or answer the question or rearrange the equation and actually do it. If you guys could count the number of times plus my 3 little bonuses, and if you could then submit that to the person that's offering $20 along with this video for anybody who can demonstrate that I can be intelligent, send me all of the $20, essentially, is what I'm saying, because it should be $20 for each time, because that was what they proposed. So
they don't feel bad. They think I'm an idiot too, and it's like, okay, that's fine, let them. I mean, but you know what? I would love to see some of these people that are detractors that have never had any math, right? Try to explain some of this stuff and try to have people try to understand it, because you know what, they don't. They're into drama, right? Their drama sells. By the way, drama will get me 10,000 more views, or 1,000 more views than what this video will get, no question about it. But I'm not interested in that. I'm just not. This is the kind of quality stuff that I want to put out. This is what
I don't even care. I just want the money. Give me my $20.
Give her the money. They won't pay you. But let me ask the live chat real quick. How many of you have ever had matrix before? In some capacity, whether it be college algebra or calculus level, higher matrix stuff, and then how many haven't? And if you haven't, being introduced to this like this, do you finally understand when people say matrix theory, kind of a little bit what they're talking about? Because Chesh had no idea about any of this before. She'd never been exposed to matrix theory. This is all new to her, So now she goes, oh, okay, this is what they mean by why we use matrix theory to solve a set of linear equations.
Correct.
So let me know in the live chat.
Grade 11, and they did not cover matrix theories. We did do some graphing, and we did balancing equations. Balancing equations actually was a little bit more in my science class. It was in chemistry, like grade 10 chemistry. But that's about it. And at no point did they ever like, oh, here, do this, balance this equation and then plot. Like, it just didn't, I don't know why. At least not that I remember. Maybe I'm wrong, and I just blocked it.
When we first started this with the demos, did it make sense to you of why like a set of linear equations has 0, 1, or infinity, right?
So when we started, I didn't even know that was a concept. If you had shown me the equation we're looking at right now, I like, especially without the numbers in it, I would have no idea what the hell I was looking at. That's Greek to me. Mm-hmm. I would not know at all. But now that we've gone through this and we spent an hour doing it, I know what that equation means.
Yeah, and that's the kind of thing. I mean, math, if you're not familiar with the symbology, and again, don't get too fixed on the symbologies for some of the stuff, because again, people use different conventions. So that's why it's part of other concepts. But we haven't ever been exposed to it before. It can be intimidating. I mean, even looking at a summation formula, right? I did a whole video on summations, and if you have never seen a sigma symbol before, you look at that going, "What the hell is this telling me? What does this do?"
An intrigued feline put an equation in the chat, and it's capital E to the power of 2 equals bracket PC bracket to the power of 2 plus bracket M bracket subscript bracket 0C to the power of 2 bracket to the power of 2.
Is that Einstein's equation?
I do not know how.
Basically, E equals MC squared when you're adding in momentum and part of the position, if I'm not mistaken.
Oh, it's for momentum. Okay, yeah. I only had.
From what I didn't see it, but from what you described, I could be totally off on that.
I've done more. I've learned, or I shouldn't say learned. I've heard more physics from watching Red's Rhetoric on YouTube than I did in high school.
Well, I mean, I want to start doing some physics stuff too. I have some physics people that want to come in too, but like for example, I know that like Dr. Cramer, we're going to talk about Lorentz contraction for special theory of relativity. I still want to do tensor math, but I don't know anything about tensor mathematics as far as like GR. I don't know that math. So.
Landon, you, and Dapper are always so patient when it comes to explaining things from like the base level to be like, okay, and now you understand it. And I'm like, yeah, now I understand.
That's where I think people should explain. Well, look, I take a very pedagogical approach to this stuff. I'm not an expert. Let me put that on the line. I'm not an expert in physics or mathematics, but I've had some physics and math training. And so I figured this, if I can explain it after 20 years, and Chesh, 62 IQ can understand it, people are without excuse then. And by the way, she says that what it is. Yeah, so I got it right, I guess.
Yeah.
You could derive E equals MC squared from it. So that's why I do this stuff. I enjoy it. It's not to make money off of it. It's not for people to like, have 1,000, 2,000 views. My math videos get by far the least amount of views, but I'd rather do those in addition to the other stuff that I do, because I know that the people that do watch these videos, they get something out of it. And that, to me, is the greatest thing on being on YouTube, is that somebody says, you know what, I watched one of Steve's videos, and I learned something I didn't know before, is great. It's just, that's what I enjoy the most.
And then it's just a matter of figuring out, where are you going to use it?
Never. You're never going to use this, people, but that's okay. At least when people talk about it, you'll know what they're talking about, right?
I actually probably will end up using it with like being on Non Sequitur and being on these shows, because it's probably going to come up again. At some point, you guys are going to be talking about some math that is way over my head, and I'm going to be like, oh, you mean like Matrix?
Yeah, well,
what's
funny?
Then somebody's going to be like, yeah, exactly like Matrix. And I'm going to be like, yeah.
What's funny is, you think about it, how many different types of subjects have we gone over that we all have to have a tertiary level understanding? I mean, I've gone from matrix theory here. I did calculus 2 before, but I've also we've done videos on like biology. We've done stuff on like human chromosome number 2 fusion site. We've done stuff on cosmology and astrophysics. I've talked with
Lawrence
Krauss about no boundary proposal from Hawking, and so there's a whole bunch of stuff that is just, you have to have a kind of a base level of a whole bunch of different topics, and it's not easy. I'm not going to front. It's not easy, but that's what I enjoy. So yeah, I'll be doing some physics stuffs too. If you guys want to do maybe free body diagrams or You want to do like we had to do like a lot of salinity type stuff where you have like a vat, we have you have a pipe going in, a pipe coming out, and you have a certain amount of flow rate going in. How much of your solution is being diluted by the water?
We're basically helping people learn how to solve the weird little equations that show up on your Facebook wall.
Yeah. I mean, maybe a lot of the stuff isn't going to probably be too useful, but if people have an interest in it, that's fine. I challenged Reds the other day to show, hey, show us how a rocket works using the actual formulas for the nozzle and efficiency and thrust and impulse, because I'd be interested in that, right?
Yeah, it would be cool to do.
Yeah. But anyways, guys, thanks for watching this. Let me know what you guys think in the comment section. Please like, subscribe, share. But more importantly, see if you can solve this yourself for the DY matrix here. And then take a picture of it and send it to me on Twitter, which is @SteveMcRae_. Yeah, do it on Twitter. It's the easiest way.
Really, Steve. Okay. Hold on.
And then I'll post them all on my wall and see who gets it right. So what I want to see is I want to see what you guys are seeing now, but I want to see it for the DY. Yeah, that's it right there. Thank you, Josh.
I'm a helper.
And by the way,
see you tomorrow.
Like I said, please leave some comments. I haven't been getting a lot of comments lately, which is kind of odd. I was getting so many before, but when I'm doing this math stuff, I don't get a lot of them because I guess people have not much to say on them. But I'd like to know what you think, one way or another. Again, not trying to be a math teacher here because I'm not as good as math as people think I am. But some of the stuff is at least in my capacity to explain. Does that make sense? Hopefully.
Yeah, well, you're saying let us know if this helped you, or if you have any questions, or if you have any equations that or have any difficulties that you'd like explained. Feel free to share this with people who are in these courses and in these classes who may benefit from it or might have anything additional to add or say or to potentially expand upon the conversation. So share it with those people and whoever you think maybe needs help in math.
Yeah, and let me know what you think you guys want a presentation on or something like that. It's something that I can do. Again, simple stuff. Let's not go hog wild. You tell me to explain the Riemann hypothesis, I'm going to probably look at you like starry eyes. There's no possible way I could do that. So, I mean, I know what it is, but I can't explain it very well. So let's keep it in the realm of reality. We're doing intro level stuff. We're not doing very complicated stuff. I mean, obviously my Taylor series stuff and my calculus stuff get a little bit complicated, but it still was not that advanced, really honestly speaking. So guys, we'll see you guys tomorrow, 11 a.m. for Caffeine Corner. I think tomorrow we're going to be doing some epistemology stuff, some virtue epistemology. And so that should be kind of interesting. And by the way, I'll get you that information. So Jess was like, what the hell are we doing tomorrow? I don't know. I never tell her 5 minutes before, hey, we're doing this. We go live. Okay.
I still want to talk about hypocrisy at some point because I feel like that is a term that needs to be explained because I see that word get thrown around a lot. And it's like, that's not, I see what you're thinking, but not quite what you're thinking.
I'm fine with that. All right, guys, we'll see you tomorrow. Good night.